Hi guys, welcome back to the 100 Days Machine Learning Crash Course. Today we are going to talk about another very interesting topic in machine learning to analyze uncertainty in pattern recognition and machine learning problems. It is called information theory. Okay. Now, we start with asking this question that what is information? Let's say we have a discrete random variable x, and we want to know that if we observe a specific event of x, how much information do we receive, and we want to quantify somehow this information. In other words, we can define information in a sense that the degree of surprise. Let me give you an example. So our purpose is to quantify, to derive a formula for information, quantify the information. Okay, now for approaching to this formula, let me give you some examples. If I tell you tomorrow sunrise, okay, tomorrow we will have sunrise, how much information does this sentence have? Really, you could say that, okay, it doesn't have so much information for me, and so about tomorrow sunrise, the information is really low and trivial. In other words, because we already know that tomorrow we will have sunrise. In other words, the probability of sunrises every day is so much high. This is the probability of having sunrise. Okay, and this is the information. Now let me give you another example. If I tell you tomorrow or 1 hour later or anything, just tomorrow, sun hits the earth. Okay, how much information does this sentence have? Okay, you could say that, oh, I am pretty shocked that tomorrow sun hits the earth. It is pretty uncommon, and so it is very informative. Why? Because so the information is pretty high for this sentence, because the probability of sun hits the earth is really low. So it seems that there is a reverse relation between the probability and information, and so this is actually one property of information formula that we want to have. And the second one is, let's say we call the formula of information h of x, which gives us the information of the random variable x. We want to, if we have two independent variables, two unrelated events, we want to have addition in the information. So for unrelated x and y, we want to have h of x and y is equal to h of x plus h of y. In other words, this is our desired result when p of x and y is equal to p of x times p of y. So because this is the condition of independency of x and y. Okay, so in this case we want to have additive information. In other words, if I tell you, okay, tomorrow, I don't know, maybe tomorrow that a student will get mark 20 in the exam, and we will have sunrise. These two information we want to add together, okay, because these two events are independent. Okay, one function that satisfies all of these nice properties is minus log of, in any, actually it could be in any basis, but sometimes it is common in communication. It is basis of 2 e of x, and this minus, if you remember from the calculus, you could write it in this way. So it means that and actually this is quantified with bits. So it means that if your event has probability close to 1, your information, which is log of 2 e of x, if this is 1, then this log will be 0. And if your probability is close to 0, then your information gets high. Okay, so the definition of information could be this. In machine learning, it is pretty common to use natural logarithm instead of basis 2. So in machine learning, we will use this formula. So it is minus ln e of x, and it is quantified by nats in comparison with bits, which has basis 2 for the log. When the basis is natural logarithm, we call it nats. Okay. Okay, now let's say we want to send this random variable which has some different states with a receiver. How much the average information do we send? Okay, so we could define the average information as 1 over n, which is for the average, then sum over all possible states of x. This is the count of one state that happens times minus log of p of x, which is the information of that state. and we know that we could include this into this and rewrite this as follows. Then we know that this is p of x, so we could write the average information as p of x log p of x. In short, we could write the average information as something like this, and we called it entropy. And it actually shows some kind of disorder. Let me give you an example. Let's say our random variable x has 8 possible states. You could think, for example, the x is some kind of alphabetical things like A, B, C, D, and E, F, G, and H. Okay, 1, 2, 3, 4, 5, 6, 7, 8. Right. Okay. So you have 8 possible states for x. And let's suppose that the probability of each state is equal, and it is equal to 1 over 8. Okay, because the sum over the probabilities should be 1, so the probability of happening each of these symbols is 1 over 8. So the entropy for this random variable is minus sum over p of x, which is 1 over 8. Maybe it is better to clarify it. It is better to write this as follows: sum over minus p of x equal to a times log p of x equal to a minus x equal to b times log p of x equal to b, and blah blah blah. Okay, now we have 8 different terms, and all of them have the same amount. So we could write this as, we know that this is 1 over 8, and this is 1 over 8. So, and we have 8 different sentences, 8 different terms. So it will be 8 times 1 over 8 log 1 over 8. So it is 3 bits. So it says that if you want to send the message for variable x, we want to send the message, we need 3 bits at least to encode A, B, C, D, E, F, G, and H. So one possibility is to assign 0, 0, 0, 0, 0, 1, 0, 1, 0, and blah 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 to all of these states. So as you could see, we need 3 bits, but we may have another encoding scheme, but it is not important for now. So if h of x is 0 means that we do not have any kind of uncertainty. You should have this intuition that to see the entropy as the uncertainty in the events. So if you don't have any kind of uncertainty, you don't have entropy. Maybe it is better to give you another example. Let's say you have a coin and the probability of head is P, and so the probability of tail is 1 minus P. Okay, so the entropy for the variable x is minus P of head times log P. It is not important, maybe 2 is better. Okay, P of head minus P of tail times log in basis 2 P of tail. Okay, if we which you could substitute these values into this equation. After that, you could plot the entropy of this variable versus the parameter P. If you plot that, you will see it has something like this. And the maximum value occurs when P is 0.5 and it is 1. What does it mean? It means that when we have the maximum entropy, it means that the probability of head and tail are equal, and they are equal to 0.5. It is the maximum uncertainty of our events. But if we know that we are in this region, it means that the probability of head is below than 0.5, means that we know that the coin is unfair, and the probability of tail is greater than 0.5. So we could guess somehow that the outcome will probably be tail. Okay, but when the probabilities are equal, we don't know actually what is the outcome. And in other words, we have the maximum uncertainty when we have some kind of uniform distribution for our possible states. Okay. Another important thing is relative entropy and mutual information. Let's say the variable x has probability distribution P of x, but we modeled it as Q of x. You could think of that P of x, it could be the data, the true distribution of data, and Q of x is the model distribution, which we find that with some kind of neural network or other possible ways. We just try to model P of x with Q of x. And now we can define a quantity which we call KL of P and Q, and we show that with this notation, and it is the difference between our modeled entropy and the true entropy of data distribution. So it will be the probability of outcomes times ln of q of x, because this is what we modeled the distribution p of x with q of x minus p of x and dx. So you should just know that in the continuous case, the entropy for variable x, if you note to this equation, this was for discrete random variable. So if we have continuous random variable, it will be the integration of p of x ln p of x dx. Okay, so this is actually the entropy of x, and we call it sometimes cross entropy between P and Q distribution. Okay, and we call the KL as Kullback Leibler divergence, or in short KL divergence. And you should note that it is not symmetrical, so the KL of P and Q is not equal to KL of Q and P. And one of the nice properties of KL is that the KL P of Q is 0 if and only if when P of X and Q of X are equal. It is so important for optimization because we could actually set KL of P and Q as our loss function. And I told you, suppose that the Q of X is a neural network and P of X is true distribution, and we want to model the true distribution with neural network. We could set the loss function as KL distance between as KL divergence between P and Q. In this case, if we could optimize and minimize this KL divergence and reach to 0, we could ensure that P is equal to Q. So we could assure that we have the right distribution now. So our model distribution is very good and it is equal to true distribution. Another nice property of KL divergence is that it is actually a convex function. Actually, we don't want to plunge into what are the convex functions, but convex functions are generally functions like this, and they are really good for optimization. So all of these can make KL divergence very good choice for setting that as a loss function. Okay, so and actually KL divergence, we will see that sometimes KL divergence could mean to some loss function that we know, so, like categorical cross entropy and other loss functions. So the origin of those loss functions are the KL divergence. Okay. Now, this was our introduction about information theory, and this is actually enough for us to know about the information theory. Okay, from the probability theory, there are some probability distributions that they are really important before we start the machine learning algorithms, and this stuff they are really important distribution to get familiar with. So we want to probability we just introduced the most important ones, but you could refer to the textbook to read about other probability distributions, which we don't introduce them in here, but they are in textbook. The first probability distribution, which is very important, is for binary variables. When we have a binary variable, for example, when we have a coin that could be head or tail, we could assign a random variable to it and call head 1 and tail 0. So this is actually a binary variable, and we could define a distribution over this random variable, and the most important and the most famous binary variable distribution is Bernoulli distribution. So Bernoulli distribution is a distribution for a binary variable, and it has one parameter mu. So the probability distribution of x given its parameter mu is equal to mu to the x times 1 minus mu to the 1 minus x, and the probability of x equal to 1 is the mu, and the mu, so it is between 0 and 1 because it is the probability of x being 1. And so Bernoulli distribution has some properties. For example, the expected value of x is mu, and the variance of x is mu times 1 minus mu. Okay. Now suppose we have a data set for this is just for clarification as some kind of example. Let's say we have a data set of x1 to xn, and each of them are observed events of random variable x, and they are IID. If we write the likelihood function, this is the likelihood function, it is equal to the product over n probability distribution of each sample. So because the samples are IID, we like for two independent variables, we had p of x times p of y for independent variables. In this case, we also convert this to the product, because this means that p of x1 and xn given mu. So because of x1, x2 and xn are IID, we could convert this to the product of these terms. Then we could substitute the formula of Bernoulli distribution for each of them, and we could derive it is equal to this. And if we go with frequentist approach, for estimating mu, we should maximize the likelihood function if we use the frequentist approach. If you remember that we talked about the maximum likelihood is when we use maximum likelihood that we have the frequentist approach. So we take the logarithm from the both sides. So we have ln of this probability, then you could write it as xn times ln of mu plus 1 minus xn times ln of 1 minus nu. So if we maximize this regarding to mu, means that you could set the derivative of this equal to 0. You will derive that the maximum likelihood estimation of the parameter mu is 1 over n, and from 1 of xn. So if the x of n is just 0 and 1, it means that it is equal to m over n if we have m1, so it is m over n. Basically it means that if we flip a coin 3 times and we observe that all of the times we have head, then the mu will be 3 over 3, which is 1. But we know that this makes no sense, because at least in common sense it is irreasonable, because the P of X is head is 1 means that the P of X is tail is 0, and this is not very logical. So this is one of the reasons that we use Bayesian approach. In Bayesian approach, we consider a prior for mu, so we will not get 1 after just 3 trial. And so this is one reason is that we use Bayesian approach instead of maximum likelihood sometimes. Okay. The extension of binary variables is that in binary case we have just 2 states. Now let's say we have k different states. For example, let's say you have a machine learning model and you want to classify between dog, cat, frog, lion, and maybe zebra. In this case, you will have 5 different states for your binary for your random variable. So in this case, you could define one way actually is to define your random variable as something like this. Let's say your input is actually a lion, so it is 0 0 0 1 0. So as you could see, the sum of the elements is 1, and so each of them are shows the probability of that class. We call this notation one hot vector, and when we want to use multi-class classification, we use the one hot vector of our classes. So if you want to have 3 different classes, you should code your output as 1 0 0 0 1 0 and 0 0 1. This is the extension of Bernoulli random variable, and in this case the probability distribution given the parameter mu is the product of mu. So this is just the extension of Bernoulli distribution, and we use it a lot. Actually, this is the most prevalent way to encode the multi-class classification labels. And the last distribution, which is very important and we use it a lot, is Gaussian distribution. The Gaussian distribution has 2 parameters, mu and sigma 2, and the formula for that is this, and we know that it has the shape something like this. But why the Gaussian distribution is so important? What are the motivations of defining this distribution. The first one is, maybe it is kind of interesting, is that the Gaussian distribution maximize the entropy when the range of x is from -infinity to infinity, and we have finite mean and variance. So for finite mean and variance, the probability distribution that maximized the entropy was this, if you forgot that. The distribution that maximizes this entropy is Gaussian distribution. And the second motivation is that if we have sum of multiple random variables, the sum of multiple random variables itself is a random variable. Let's say we have x1, x2, and x3. x1, x2, and x3 is each of them is a random variable. So sum of them itself, let's call that y. The y itself is a random variable, and the distribution of the y, if the number of this sum goes up, the probability distribution of y will be close to Gaussian distribution. And maybe you heard that we call this theorem central limit theorem, or CLT. So let's say when you have just only one x1 and x1 has uniform distribution, you will have something like this. Then if you increase the number of variables and x1 and x2 has uniform variables, you will have something like this. By increasing the number of this sum, for example, in n equal to 12, you will have something like this. It is not completely Gaussian, but it will be close. And then when n will be infinity, then you will have Gaussian distribution for the sum of these. For the distribution of y, which is a sum over all of x. So until now we learned about all fundamentals that we need to learn about the machine learning algorithms for regression and classification problems, and yeah, and from the next session we will start the regression algorithms, and probably they will they will be more practical algorithms than these basics, because these basics are more about the theory, analytics of our problems that we will face. But from the next session we will learn about the practical algorithms. So hope to see you in the next session. Bye.